welcome back. So for our second talk this morning, we have Kristine Bauer from the University of Calgary giving the first of our 3 talks on Introduction to Functor Calculus.
Thank you all for being here. I'd like to thank the organizers for inviting me, and I have to tell you that I'm just incredibly humbled to be giving this introduction. A little more than 20 years ago, I was at a London Math Society summer school, or some kind of school that Tom Goodwillie gave, and I learned a lot of this material in those lectures. And in the intervening time, it's been taught many times by some people who are even in this room. So I'm just incredibly grateful to have the opportunity to do this myself and to have you all here to witness it. Okay, so there used to be a picture of tulips here, which I'll tell you about after I tell you what the QR code is. So I have some handwritten notes, and because this is a hybrid lecture, I know it can be difficult to keep up with what's happening on the slides. If I were giving a chalk talk, it would be possible to take notes, but I'm not giving a chalk talk, and I don't think it will be possible to take notes. So if you would like to follow along with my notes, that's how you get to them. They're not perfect. I'm not trying to say that this is anything that should be published, but this is something that might make it easier to endure the talks. Oh, right. What was the tulips for? Because when I should have been spending a lot of time making these really beautiful slides, instead I was at Kew Gardens getting sunburned. And so I was going to share those tulips with you. But also, tulips are amongst the first flowers in a garden to bloom. They come up very quickly, and then their blooms die back. And a lot of gardeners struggle with what to do with the greenery after the blooms have gone because they're not so pretty anymore. A master gardener will use those greens to build structure in a garden. So I hope that these introductory talks are something like that. They come first. They're going to be something that I hope will spark very quickly and bloom. And then if we do it right, this should be the foundation for some of the other talks that will happen at this conference. Okay. All right, so I'm a little bit motivated by this book, Experiencing Geometry by Henderson and Tamina. Some of you will know about Tamina's crocheted hyperbolic planes. This is the textbook that came out of that. And this book was written with a different perspective in mind. To get everybody on the same page, they asked the question first, what does it even mean to be geometry? And as basic as what does it even mean to be a straight line? And that helps to make sure that we're all on the same page. I don't know you, many of you, and you don't know me, many of you. So I thought maybe we could start with a similar kind of exercise. And my questions are not geometric, they're more algebraic in nature. So what I'd like to do is start by asking you to think a little bit about what linearity actually is. So this isn't meant to be a difficult question. What do we tell our students a linear function is in calculus and linear algebra? What are the properties of those linear functions? And what I'd encourage you to think about are things that are intrinsic. Don't be thinking about something where it turns out that you have to know something more complicated, like what a polynomial is, to talk about what linear is. What are the kind of intrinsic properties of what it means to be linear? Okay, so this is the audience participation part. And Florian, I have you monitoring the chat. So if you're not in the room, there is somebody here who will be able to kind of share your thoughts. What would you tell your students?
Sorry, what was the question?
What would you tell your students a linear function is in calculus or linear algebra? And what properties do those functions have?
To distribute.
Distribute. So I think when you say distribute, you mean something like this. F of ax plus by is af of x plus bf of y for some coefficients. So if I were in linear algebra and we had vector spaces with appropriate scalars a and b, this would be a linear function. Great. Did anybody think of a different answer when they were thinking about linear functions?
Maybe constant derivative.
Constant derivative. Anything else?
Thank you. Just going to say f of x is ax, maybe with plus b, depending on what will be learned.
How about we use different letters? I guess I used a B, so we'll use a D. Okay, yeah.
They respect parallel, parallelism, is that a word? They like respect like.
Translations. So I don't know how I wanna write this, so, so let's, it's not transport, it's translation. And I'm not quite sure what I wanna say. So I think that's enough for us to get started. The main thing here is that some of these properties are really very different from one another, and there are choices involved. So I expected, something about linearity in terms of the kind of linear algebra course version of linearity, which means that you respect sums somehow. And I expected that linear functions have a constant slope or derivative or rate of change, which we've also recorded. And I'm going to try in these lectures to talk to you about both of these perspectives on what linear functions are. I would say that I'm not going to focus on the geometric side very much. So it is possible for us to think about lines in terms of geometry, but that's not a thing I'm going to do. And what I want is to try to use generalizations of these, not to talk about linear functions anymore, but instead to describe linear functors. The important thing to remember is that right at the beginning, we already have choices made about what linearity means. And so I'm going to start out with a particular choice of excision as linearity. Now, functor calculus has been around for a long time now. So these are some of the first papers on functor calculus. And there are many different flavors of functor calculus. Even from the beginning, there were a lot of different flavors of functor calculus. And a lot of those can be boiled down to the choice of what you think a linear functor is from the beginning. But I thought it would be too confusing to try to tell you all of the different ways that functors can be linear at once. So we're going to stick with one. And I'm going to choose excision as the way that I go for what it means to be linear. And that means that I'm basically following the course set out by Goodwillie in Calculus 1, 2, and 3. So if you want to know more about the things that I say in these lectures, that's where to go. If you prefer to think about infinity categories instead of categories, then I'll also be from time to time talking about things that appear in chapter 6 of higher algebra, which is very much the same perspective. So for the remainder of this talk, what I want to be doing is mostly talking about categories and non-infinity categories. And I'm going to be talking about functors from a category C to a category D. My category C, I need to be able to take finite colimits. And I want everybody in sight to have a base point. My category D, I'm going to need to take finite limits, but also sequential colimits. And I also want that one to have a base point, and I also want that one to be homotopical. So when it turns out that I don't want things to be too general, I'm really talking about based functors of base spaces. So for the most part, if it turns out that you don't want to think in this level of generality, there should be no problem thinking just about the category top. And sometimes I'm going to have to be in top because of the way that I want to present things. All right. So a functor is called excisive if it sends strict push-out diagrams to homotopy pullback diagrams. In other words, it's not so easy to write on an iPad while you're trying to talk to a group of people. So excuse the fuzziness. This isn't, the pencil is wavering a little bit more than it usually does. So if I start out with a diagram like this, which happens to be a push-out diagram, then I'm going to hit the whole thing with F. Including the maps, which I didn't take the time to name. So maybe this map might be named little b, then this would be f of little b. You could name all of the maps if you want to, that's just notation. And I'm going to ask not that this is a strict push-out diagram, but that this is a homotopy push-out diagram. So those pullback, sorry, I said push-out, I meant pullback. Okay, and as I said, this notion of linearity is going to produce Goodwillie's calculus. Let me just make sure that there wasn't anything else I wanted to say there. So this is a push-up. I see that there's a flaw in my plan. Okay, so this is a push-up. And this is a homotopy pullback. So we've got a couple of things that we have to pull apart in this slide. One is, why is excision a good choice for what we mean by linearity? And the other is, I just said homotopy pullback. And maybe I should tell you something about what I mean by those. Okay. So the key example of somebody who is excisive is homology. So this is just going to be our reduced singular homology functor, and let's just start with a really canonical pushout diagram, which expresses a space as a union of two subspaces A and B. So I glue those together along their intersection. This is a very nice pushout diagram. Now, in the case that A intersect B is trivial, then this pushout diagram, well, in that case, this is just a point, and this, of course, is just the wedge of two spaces, usually written this way instead of with a union. And in this case, when I hit this with homology, what I end up getting is the reduced homology of a point, mapping to the reduced homology of A, the reduced homology of B, and the reduced homology of the wedge. And this, in fact, is, if I'm thinking about reduced homology as a functor to graded groups, this is actually a strict pullback, not just a pullback diagram. And the reason it's a pullback is exactly because of the fact that this is an additive functor, so that this is the same thing as the homology of A plus the homology of B. So the first reason that excision might be a good idea is because it does something like what we did when it turned out we had linear functions. Given a prescribed way to add two things together, I have a prescribed way of adding together the result. That's exactly what we did when we were talking about linear functions. Okay, so in this case, it's actually just precisely what we would think it would be. It's a little bit misleading because in the category of abelian groups, that sum is a byproduct. And so I don't know yet if what I want there is to think about that as a coproduct or a product. But if I want to think about this diagram as a pullback, it turns out that the product is the way that is going to be the thing that I'm thinking about. Okay. Now, of course, this also, just to say what excision is, in the general case, when I hit this diagram with H, this is a pullback. If and only if the reduced homology groups B relative A union A intersect B mapping to A union B rel A is an isomorphism, which of course is the usual statement of excision. So so we might wrap up the whole thing there by saying, okay, great. So the fact that this was an excisive functor, taking pushouts to pullbacks, gave me the additive property that I was looking for. And it also gives me the thing that I usually think about when I'm thinking about a homology excision. So I've got a really nice starting point here in thinking about linearity as excision. All right, so that's the end of our first digression. That's going to be the reason that we want to think about excision. One example that gives us a reason to think about excision as linearity. Okay, oh, and I even have a slide that says, so excision tells us something about the behavior of functions on sums, thought of as pushouts. Excision takes pushouts to pullbacks. Pullbacks are fiber products, so we're really thinking about a product thing here. And it's also reasonable to interpret addition on the outside as a product. And then finally, I just want to say once again that this interpretation of linearity is a choice. And in lecture 3, I will show you some other choices, but we'll wait until we get there. Okay. All right, the second thing is that I said homotopy pullback, and I think it's a good idea for a minute just to talk about what it is that I mean by that. So the homotopy pullback is meant to be the best cone over a diagram invariant under homotopy equivalence. But it doesn't satisfy a universal property, and taking that idea of what it means to be a homotopy pullback is not going to be helpful in terms of an actual definition. So in these lectures, one of the reasons that I will be thinking about functors from spaces to spaces is so that I can give you an actual concrete construction of what I mean by the homotopy pullback. And I'm going to need it in a few instances. So in general, I could construct this in other categories. I'm sorry, because I see that I have a, my pen is just a little bit in the way. Let's try that. Okay. So to give a precise construction of a homotopy pullback requires us to have more specific information. I could be working in an infinity category. I could be working in general in a model category where I would probably do something like take a fiber replacement of a diagram and take a strict pullback. But I maybe want to have a very concrete way of doing that, which is the case in spaces. So I have a very specific replacement in mind. And when I'm in topological spaces, what I want to do is probably a familiar construction to most of you, but in case you haven't seen it, I'll take a diagram with B mapping to D and C mapping to D, and I'm going to replace B by the path space of the map B. So this is just the space of pairs, B gamma, where B is a point in B, and gamma is a path from I to D, such that gamma of 1 is equal to, see, I've made a mistake. My points are usually named with lowercase letters, but in this case, I named them maps. So this should be B of X. And then I'm going to send this by evaluation of gamma of 0 to D. It was, after all, a path in D, and I'm just deforming B of X homotopically to wherever the other endpoint of that path is. And then I can do the same thing at the other side if I want to. And then take the strict pullback. Let's just call that X. Okay, so the strict pullback of this diagram is the homotopy pullback. Can't quite fit it, pullback. Okay, so, yeah, good enough. And then I can complete this diagram this way to make it clear that that's what I mean. Okay. Yeah.
I might miss this number. Why do we say we want to send push-ups to pullbacks as opposed to push-ups again? Like if I just did 9.
That's one of the choices that I was talking about. So sending pushouts to pullback is a choice in linearity. So we could ask instead that a functor preserves pushouts or co-products, or it preserves pullbacks or products, or it could do a number of other things. Those all lead to some notion of calculus, but they're all different. So I'm staying with this one because this is the one that gives us the statement of excision. That's the classical excision statement for a singular homology and for a generalized homology domains. Okay. But you're right, I didn't have to. It's a choice.
Do you know what happens if you send push-up and push-out?
Yep.
Yeah, like a good answer to the.
Come back on Thursday. Okay, so great. So this is the homotopy pullback. Okay, so in particular, all I want to say here is that if I do this same construction, in the case, let's call this map little t. If I do this same construction in the case where it turns out that I have points here, the only thing I want to point out, you can do this however you want to do this. I'm not going to do the details. Is that what I get as my homotopy pullback is the loop space on T. Okay, so far so good. All right, so those were a couple of digressions, and let's get back to what we were talking about. So I have defined excision. So a functor is excisive if it sends pushouts to pullbacks. If it also happens to satisfy, remember everybody in sight was base pointed. So if it happens to satisfy the property that f of the base point of C is the base point of D, which isn't always the case, but we'll impose it from time to time, then we say the functor is called reduced. And if a functor is both reduced and excisive, then it's called linear. So this is the full definition of what it is that I mean by linearity. What did I do wrong? Oh, okay.
I'm just a little bit wondering why you say strict push out to homotopy pullback.
Yeah, so I have a choice and I could have said just homotopy pushouts to homotopy pullbacks. But I'm going to always arrange to have a strict push out in this talk. That's all. Okay, so this is it's another choice, but you're right. I don't have to do it that way. Maybe I should also say very quickly while we're talking about homotopy pullbacks, because later I will say homotopy co-limits or something like it, that this path space construction has a dual, it's the mapping cone. And of course, I could always do the same kind of thing by replacing a diagram using not mapping cone, mapping cylinder. Using the mapping cylinder, I could replace an entire diagram, take a strict co-limit, and then I would get a model for homotopy co-limits. We'll use that a little bit later as well. And so Greg is just asking, why didn't I do that right away? Just because I wanted to save it for later. All right. All right, so not only is reduced singular homology excisive, but by definition, any generalized homology theory is excisive. Generalized homology theories satisfy 6 axioms, depending on how you count, and one of those is always excision. And for any generalized homology theory, then in fact, for any functor at all, doesn't have to be a generalized homology theory, I can always define its reduction by taking the functor f of x, and as long as I'm able to make quotients, I could mod out by, I see that you can't see that because of the shadow. I'll just put it down here. As long as I can take quotients, I can always just kill the value at the base point. And there you go. From any functor, we've created a reduced functor. And if E is a spectrum, then as another example, E smash X is linear. And if you believe Brown representability theory, which I hope you do, then those in fact are the same example. Okay. Okay. Great. So now that we've agreed what it means to be linear, I want to show you how to construct the linear approximation. So this construction is going to happen in 2 steps. And what we're going to do first is try to take a functor that makes something slightly closer to being a linear functor. So what I'll do is I'll start with this pushout diagram. So Greg asked why I started with strict pushouts. It's because I'm starting with a diagram which happens to be the homotopy pushout of something else. So in this diagram, I've started with a space X, which is an arbitrary space. Now I'm dealing strictly with topological spaces, by the way. Okay, so I've taken a space X, I formed its cone, I include X into the base of the cone. I do that twice. I take the pushout, I've glued 2 cones along each other. If I hadn't said strict pushout, I could notice that this is the same thing as just a point, and then I could have taken a homotopy pushout instead. Okay, so I arranged this so that I don't have to do that. All right, now my functor f is the thing that I'm interested in, so I want to go ahead and hit and apply f to this entire diagram. Okay, suppose that f is reduced already. So then what I'm worried about here is trying to figure out how to bring F closer to being excisive. Well, if F is reduced, then this thing, and it's a homotopy functor. This thing is equivalent to F of a point, and that is equivalent to a point. The same here. So this is the diagram that we just talked about, and when I take the pullback, which will be the homotopy pullback of the thing that I get by deleting F of X, then what I get is going to be loops F of suspension X. Okay, now, the suspension here is the unreduced suspension. It's just the union of two cones along a common copy of X. But that's homotopy equivalent to the regular suspension. So if you prefer to have a base version of your suspension, then you get that. All right, so here's the pullback of that diagram. This is the homotopy pullback of the thing that I started with. And from this, what I get is a unique map Fx to loop F suspension X. All right, so let's let TF be the homotopy pullback of the diagram. In other words, loop F suspension of whatever space I started with. Everything that we did here was functorial. Taking homotopy pullbacks is functorial. And so this construction produces a functor TF. And on top of that, the existence of the natural map from F of X into loop F suspension X is natural in X. And so what we've just done is produce a functor TF and a natural transformation, which I'll call little t, from F to TF. Okay, so I claim that that's going to get us a little bit closer to being excisive, and towards the end of this talk, I'll show you exactly why this is slightly more excisive than the functor that we started with. But first, I'm going to finish the construction. So this was step 1 of constructing a linear approximation. And step 2 is to realize that I can iterate. So if I iterate the construction of T, then what I do is produce a whole tower. So this is our little t map. This is little t applied to the functor t, little t applied to the functor t squared, and so on and so forth. Okay, so now is the point where I'm going to take the homotopy colimit, do whatever you would like to replace that diagram, and take the homotopy colimit of everything there is natural. So I'm taking a homotopy colimit of these as functors, and the resulting thing is called P1. Now, because I had this natural map F into this tower to begin with, that means that I also get a natural map P1F, which is a natural transformation from F into the homotopy colimit. All right. So at that point, I think that we've done our linear approximation. So if, right, so I forgot to talk about the fact that this was linear. So note, PF of a point is loops F suspension of a point. But the suspension of point is just a point. This thing is just homotopy equivalent to a point. So if F is reduced, then P1F is reduced. And I should only call this linear approximation in that case. What I've got is something that's excisive. If F wasn't reduced, then P1F isn't necessarily reduced. Okay, so I'm going to prove a simplified version of this theorem that says that P1F is excisive. And to do this, we're just going to use some notions of connectivity. That's the reason I wanted to work in topological spaces to begin with. So just to remind you, and also because sometimes there is a shift of index, a space X is K connected if its first K plus 1 homotopy groups are trivial. So in other words, this is trivial for all values of star between 0 and k, including saying that there's only one path component. A map is k connected if it's an isomorphism between in the range from 0 to k minus 1. And this obviously has a typo. Somebody forgot to put a backslash. So the map between pi k x and pi k of the point is surjective. Sorry, pi k y is surjective. The last translation is the one that I just said. A space x is k connected if and only if the map from x to the point is k plus 1 connected. Okay. All right, so the simplified version that I'm going to show you of the proof that P1F is excisive uses something called stable excision or a functor being stably excisive. So suppose that there's a constant capital K. I hope that capital K looks like a capital K the whole way through, and a constant C. So that for every pushout diagram with maps, the pushout of F and G, if F is K1 connected, and G is K2 connected, then what I want is that when I apply F to the entire diagram, remember, this might not be a pullback diagram, but I can take its homotopy pullback. That's this homotopy limit. And what I want, and of course, this outer diagram will commute still because F is a functor. So what I want is that this map is K1 plus K2 plus C connected. Okay, so if F has a constant K and a constant C that satisfy this, then F is stably excisive with constants K and C. So what I want to do now is assume that F has this kind of connectivity. So it tells me that F isn't itself excisive, but it's kind of excisive in a range. So if I know the connectivity of these, then it's equivalent to being the homotopy pullback in this range. And what I want to show you is that the functor P1, the functor T that I defined to begin with as my helping functor, if F is stably excisive with constants K and C, then T is slightly more excisive. That constant C is going to increase. All right. So that's what I meant when I said before that T was slightly more excisive. All right. So here's the statement of the theorem. So if F is stably excisive with constants K and C, then TF is going to be, stably excisive with constants K and C plus 1. And as a result, P1 will be excisive. Because the idea is that as I continue iterating, I'll keep making it so that that constant C increases. In the limit, it's excisive. Okay, so the first thing to note is that 2 is a consequence of 1. And now I want to just give you an idea of the proof. With that, I want to consult my notes, but we've gone very far down. Okay. All right, so suppose that X is connected, is K connected. In other words, I have a map, my map to the terminal object, and that one is going to be K plus 1 connected. Okay, well, then the suspension of X is more connected. It's at least K plus 2 connected in this case. So if I want to say that as a map, mostly because I kept losing track of my indices, this is going to be K plus, sorry, I only increased the connectivity by 1, and there you go, that's why I have to write it both times. This is K plus 2 connected. Okay, so the suspension increases the connectivity by 1. Great, okay. And then as a quick aside, if I had a map which was an if I have a map from A to B, which is an isomorphism, then let's just check and see so if this is an isomorphism when star is less than or equal to n, then I just want to check and see what happens when it turns out I'm looking at loops instead. And this is mostly just to keep track of what's happening again with that index. Nope. Okay, so this is so I have a map from A to B, and then I have an induced map from loops A to loops B. And I look at the induced map on homotopy for both of these. If the top one was an isomorphism for star less than or equal to n, then this one is an isomorphism for star plus 1 less than or equal to n, or star less than or equal to n minus 1. And that's because, of course, this is just the same thing as the original map, but with a shifted index. Okay. So we have this little shift, and now we can do everything that we need to do. So note that if X is K connected, sorry, what did I say X was to begin with? Yeah, K connected. And if K is greater than whatever the K was, capital K was that I set out to begin with. I think I was supposed to be being very careful to make sure that this was a lowercase k. Then gotten lost in my notes. All right, so then I have a push-out diagram in which this is K connected and this is K connected. And I've assumed that F is stably excisive. So that means that F of X to the homotopy pullback of this diagram, well, that's TF. This is going to be 2K plus C connected. And the part of this proof that I wanted to show you is that now if I try this with T, it's going now T is going to be even more connected. So as a result of this, I look at TF of X and I ask, how connected are you to the next one in the chain? But this is loop F of suspension X. And this is loop squared F of suspension squared X. And what I notice is that if I had repeated this entire diagram with the suspension instead, then these new maps are now K plus 1 connected instead of K connected, meaning that the map from F of suspension X to its T, which is just loop F of suspension squared X, this thing is going to be 2 times k plus 1 plus c connected. Right, and so I set all of this up to make it so I didn't fall into this trap, and then look, I did it. So this one was k plus 1 connected. And this one is supposed to be 2 k plus 1 plus c connected. And this one is k plus 2 connected. So this is supposed to be 2 k plus 2 plus c connected. And the point is that when I now look at what happens when I loop that map, this one is supposed to be 2 k plus 1, k plus 2, let's not do it again, plus c minus 1 connected, which is equal to 2 k plus 1 plus c plus 1. So the connectivity has increased by 1. So this is only a step of the proof to show that in fact that means that TF is going to be stably excisive with constants capital K and C plus 1, but it's enough to believe that this is what's happening. So as we go through this tower, if I start with somebody that's stably excisive, then I produce somebody at the end who's going to be all the way excisive. Okay. All right, so that's enough reason to say that P1F is a linear approximation, if it turns out that F was reduced to begin with. But what I want to be doing, maybe I want to write a summary of this somewhere. I can't because I didn't leave myself quite enough space for that. But in fact, it should be an approximation as well, in the sense that it shouldn't just be an approximation. It shouldn't just be any approximation. It should somehow be the best approximation. So to talk about that, what I want to know is that P1F is universal. So it's not just that it's, you know, I made it out of F and it turns out to be excisive. I also want to know that it's somehow closest. So by being universal, what I mean is that I want the natural transformation from F to P1F to be the universal map in the homotopy category, from F to an excisive functor. In other words, two things. So one, if I have any other natural transformation sigma from F to an excisive functor G, then sigma factors through. The natural transformation P1F, little P1F. That's the first thing, is that it factors through. And the second part of it is that it does so uniquely. Okay, so let's show first that it factors. So suppose that I have my sigma. And now let's look at P1 little f of both of these. So the problem with doing things this way is that it's always hard to tell who's a lowercase letter and who's an uppercase letter. So the maps are little p's and the functors are big P's. And I have a nice map here, which is the induced map on sigma. Okay, everything I did when I formed P1 was functorial, which means in particular was also functorial in the F. And so if I have a natural transformation from F to G, I get a natural transformation from P1F to P1G. Okay, now G is excisive. So what does the map P1G do? Well, I didn't really show you this, but if I started with an excisive functor G, then when I form T, I just get G back again, because G itself took strict pushouts to homotopy pullbacks, which means that the map from G to T of G was an equivalence. So this map is gonna be an equivalence. And so the factoring through, the reason it happens in the homotopy category is because I can think of that factorization as happening right there by inverting P1G, then I get a nice map from P1F to G. Okay, so there exists a factorization. And then the second thing that I want to do is note that that thing is basically unique. And so I could ask, that the only way that I could get this thing, which maybe I'll give this one a different name now, I'm gonna call this new. What I want to know is that new is completely determined by tau, by, I didn't call it tau here. I want to make sure that it is determined by this composition, which is called sigma. There we go. I called it tau in my notes. Okay. So how do I know that that turns out to be true? Well, let's start with F. We'll form P1F. And here's my natural transformation. New. That was the diagonal of the previous map to G. I'm going to hit this entire thing with the functor P1. This will be little P1F. This is little P1 of P1F. And this is little P1 of G, just like it was before. And I applied a functor, so this is P1 of little P1 of F. And this is P1 new. Okay. Well, just like before, this is a weak equivalence because G was already excisive. This is a weak equivalence because P1F is already excisive. At least I proved that when F is in the stable range. I'll talk to you tomorrow about why it's true in general. And we're going to assume that result for now. And then finally, this one is also an equivalence, basically because P1F is excisive. So from this, I know that new is determined by P1 new. Because it's what I get by going around the diagram this way. But P1 new is determined by the composite P1 little P1F composed with P1 new, because this one's a weak equivalence. And then finally, P1 of P1F composed with P1 new is equal to P1 of P1F composed with new. And of course, that is determined by P1F composed with new, because big P1 is a functor, and that's what I wanted. So that's the uniqueness. Okay, so what we've done today is talk about the fact that P1F is excisive. So we're going to use excisive as our definition of linear. We've produced a linear approximation to a functor F. And we showed that, in fact, this thing is an approximation in the sense of being universal. So that's as much as I want to try to get done today. What I want to show you tomorrow is that, well, I restricted topological spaces here, but I didn't have to. So I'm going to show you how to talk in general, more generally about this tomorrow, especially if you want to talk about infinity categories. And this is just the first stage of a tower. So where we're going from here is that we might want to talk about functors being excisive because they're easier to compute. We might want to talk about approximating a functor by a linear functor the way that I showed you here. But in fact, that approximation gets a lot better. And where I want to go with this is to show you that, in fact, this is not just a linear approximation, but it's the first stage of something that can reasonably be called a Taylor tower. That's what we're going to do tomorrow. Okay, thanks. We'll start here. I think we started to try to ask me a question and I was lost in my iPad.
That was
Yeah.
literally just like, I was confused, but that wouldn't matter. No, I was just curious if you had a slogan about like kind of what type of data the map T forgets, or if like thinking of it as like forgetting data is like even the right way to think about this. And especially like in terms of like what I'm forgetting, like each time I iterate it in that tower to get P1.
I guess I'm thinking more about the fact that about what it remembers as opposed to what it forgets. So it's exactly as I've been saying. So T remembers a little bit more about how to be excisive than F did. So it's something that's trying hard to when you take the pullback of one of those strict push-out diagrams, trying to remember how connected that map is to the actual pullback. So it's remembering more information. But when you do that, you of course killed a little bit of F. There's another way that I want to, so people who know me know that I think a little bit more about, yeah, okay, there's a way to think about it, forgetting. I tend to think a little bit more about abelian functor calculus than homotopy functor calculus. And in abelian functor calculus at the very beginning, you just measure the difference. How close was F to taking, in that case, a coproduct to a product? So that thing has a name, it's a cross effect. We have that in homotopy calculus too. And you are doing your best to kill the cross effect, which is the part that didn't know how to be excisive. But when you do that, taking quotients is not always a nice homotopy operation. So in abelian functor calculus especially, you have to do something more. So you can't just take that quotient, you have to do something to make it homotopic, something to make it behave properly. And so that's what T is trying to do. And what P1 successfully does is it kills the difference between F being excisive and not being excisive. How close was that to F? Well, that's what the tower's for. You might have done something fairly destructive to F, but then as we go through the tower, maybe you'll see ways to build that back in. And we hope that in extreme cases that the tower converges and in fact you get F back.
I guess building on what the question was previously, what kinds of properties do we see preserved in this first stage, like of F, in some typical examples of when you want to do this?
Well, thinking about singular homology as our property, we certainly want to think about this as being a homotopy functor. I didn't really talk about the fact that I guess I did. Everything we did is a homotopy construction. So we still get something that's a homotopy functor. And if it turns out we're stably excisive, in fact, it's the same functor in a range. And then after that, it's going to be different. So that's, maybe I've got the range backwards, sorry. So it's the same functor in a range, but it's the wrong range. I'm sorry, I'm not answering your question very well. But yeah, it's definitely going to have a comparison functor, and you can ask how connected that functor is and go from there.
So connectivity is one of the key characteristics we're caring about, and
so it's a way of, yeah, so in general, I want to think about this just as being a natural transformation. And connectivity is useful when it turns out we're talking about functors from spaces to spaces. If I want to do things more generally, then I won't have that in general, but I can still ask about, for example, a fiber of a map or a co-fiber of a map. And those things are going to measure the difference between those two things. And we can control the fiber and co-fiber in ways that you'll see a little bit more tomorrow, so that's the part that we really want to get at. In the best case, if I'm thinking about trying to build up a tower, then I'll start at the bottom of when I start to build a tower, again, tomorrow, I'll start with f of a point, and I'll have P1 f of x. And I can ask what the difference is. That thing's gonna be called D1 f of x. Ideally, P1 f of x would be a sum of these two. If I were dealing with actual Taylor series of functions, then I would be able to say that my linear approximation is the constant value plus a strictly linear term, which I haven't defined yet, so I'm sorry, that's where your question is coming from, because I haven't actually done this yet. So ideally, these would just be a sum. Maybe it's not a sum because maybe it turns out there's some kind of extension data or something like that. But at least I would know how to make those comparisons and I get a little bit of control over what's happening on those fibers. So I will do that a little bit more in my next lecture and you'll see a little bit more about what the difference is. Yeah.
How do you define T1? It's not reduced.
How do you do it if it turns out it's not reduced?
Yes.
Do everything that I did, but don't say linear. Just say excisive. So there's nothing in these constructions that made it so that what I'm getting is meant to be a linear approximation. It's really meant to be an excisive approximation. I think I got a little hung up on using the word linear approximation because of the fact that in calculus of a real variable, we talk about linear approximation so much. Okay, but if it turns out it's not reduced, then you can do what I showed you earlier, which is you can just take the reduction, so that F tilde operation, and then you can apply P1 to that. Then you'll get something that's fully linear, but I think that that's actually a little bit of a red herring. What we really wanted was, what I should have said here was that we were trying to produce the best excisive approximation, and that's good enough. Okay. The linear part will end up being this guy, which has killed off the base point. Yeah.
Of the 4 notions of linearity you wrote down on the board, I feel like this gives a satisfactory answer for the first one. The second one maybe will be when you define D1. The third one is close enough to the first one that I'm okay.
Oh, this one I would have thought of as close enough to this one.
Yeah.
That it has a kind of constant slope or constant rate of change. And the only difference that I see between this one and the other two is that in linear algebra, we maybe would talk about this as being the span of a vector, no location. So we force it to go through 0. This one didn't have to go through 0. And so the difference is really just whether or not I'm going to think about things being, as I've been thinking about things being reduced or not. And that's it. So it's just location. Yeah.
And my question is, at the risk of being a bit stubborn, given what you said at the beginning of the talk, is there any perspective on the last one that we can use of like I've heard that linear objects could be like the invertible ones if there's some noidal something or anything, like is there something that it preserves lines?
Well, so I don't know if I can think about how it's going to preserve lines, but certainly in terms of thinking about it being the span of a single object. That's a thing that we can absolutely do. And then again, if I want to think about something being strictly linear, this actually, I mean, neither one of these is strictly linear in the way that I said, because neither one of them goes through the origin. And so maybe I want to try to stick with some of these properties about how it acts on sums to make it so that I'm thinking about that. And then I get something that I can start to think about what's happening when it turns out I do some kind of transport. So I can start with functor. This is very much what I did when it turns out I made the reduced functor. So I can start with a functor that's excisive and reduced, it goes through the origin. And then I can ask, well, what if I didn't want it to go in the origin? The opposite of the process that I did when I took F tilde, where I killed the base point, is add it back in by a coproduct. That's my version of parallel transport. And yes, in that case, if I started with something linear, I produced something excisive, but no longer with f of 0 equals 0. And that will work.
Questions?